Hi, my name is Daniel Levy, and I'm here with Mark Luberman. And today we'll be telling you about the Reynolds number and how it has other applications outside of fluid mechanics. The Reynolds number was created by Osborne Reynolds, who is an English engineer and physicist, best known for his work in the fields of hydraulics and hydrodynamics. He was born in 1842 in Belfast, Ireland, and died in 1912. His classic paper on the law of resistance in parallel channels investigated the transition from smooth or laminar to turbulent flow, which led to his discovery of the Reynolds number, a way to describe the state of a flow.
What this number that he found represents is the inertial force over the viscous force. To calculate this, you could do it two ways. The first way is using dynamic viscosity. Here we have the density times the velocity times the length divided by dynamic viscosity is the Reynolds number. Or we could substitute in the kinematic viscosity, being the kinematic viscosity is equal to density divided by dynamic viscosity, which would give us the above equation. When you do all these terms together, what you find is that the force, length, and time terms all cancel out to zero, making this a dimensionless number. Being it's a dimensionless number, this turns out to be a frequent pi term that we found in this class as well as others, such as the Euler number and Froude number. The Reynolds number is up there with it.
In theory, the Reynolds number is a way to determine whether the flow is turbulent or laminar. At large Reynolds numbers, the inertia forces are very large compared to the viscous forces, resulting in a random and rapid fluctuations known as eddies, which lead to turbulent flow. At a small Reynolds numbers, the viscous forces are able to contain the inertia forces, resulting in a controlled uniform flow known as laminar flow. In this class, we are focused on fluid mechanics, but Reynolds number is a very important factor also in heat and mass transfer. The eddies and turbulence flow, which are the rapid fluctuations of swirling regions in the fluid, are a good mechanism for heat and mass transfer. This is because these eddies transport energy to other regions of the flow in many different directions at a quick rate, which greatly enhance heat and mass transfer compared to laminar flow. Laminar flow heat and mass transfer is traveled along by molecular diffusion, which is simply the movement of particles through a fluid, which basically lacks the additional mechanism of eddies. This is why turbulent flow has the energy required to travel upstream, where laminar flow can only travel in one direction.
What we use the Reynolds number for is in the new equation. The new equation is a function of the Reynolds number and the Prandtl number, and is used to describe the geometry and type of flow over a given area. The type of flow is determined using the Reynolds number being if, for example, for external flows over a flat plate, if the Reynolds number is less than 5 times 10 to the 5th, we have a laminar flow. What this flow and geometry would give us is a new equation of 0.664 times the Reynolds number to the 1/2 times the Prandtl number to the 1/3. What we then do from this is find the convection coefficient, commonly referred to as h. By setting nu equals the convection coefficient times the diameter or length, depending on if it's a flat plate or a sphere or a different type of geometry, and dividing it by the thermal conductivity, we get an h value which can lead to things such as the rate of heat or mass flux by convection over a substance. What this shows is that the Reynolds number is not only used for fluids, but it could be used for things such as heat and mass transfer flux, making it a very important topic to determine flow.